Here is another classic Ampere problem that I wanted to share with you. So the chart or the object that we're given here is an infinite conducting sheet. So we're just looking at a cross section of it. It's infinite, but because, the page is not infinite, we've just drawn a piece of it here, but assume that it is infinite. And we're looking at a cross section of it. The linear current density is given as lambda. And so lambda. And the current is coming out of the page as shown there. So we want to do a couple things here. First, we want to just be sure we can confirm the B field directions that are shown and give us a feeling for what the B field would look like for this kind of object. And then we're actually going to be finding the field at those points using Ampere's law. So first, to just confirm the direction. So you can think about this sheet as like a summation of a whole bunch of adjacent wires. So like what would happen if you had a whole bunch of wires just all sitting right next to each other, and those wires were all carrying current out of the page? I'm going to draw a little kind of diagram to the side over here so we can just have that conversation for a second. So here, this would be like a whole bunch of wires, right? Where that's how we're thinking about this sheet sitting right next to each other. And I can consider the B field due to two of the wires, and then I can extrapolate that argument to all the wires, but I'll just consider two of the wires. So I know that I'm looking at concentric circles, right? And I'm just going to draw two that are going to be overlapping. We have current out of the page, so that gives us anti-clockwise direction for our B field here. Okay, now what I want you to think about is the point at which those circles overlap, because that's where the summation is going to happen. So if I look at that here, I'll look at the top point where those circles overlap, and that will be this direction. I'm trying to draw this arrow in down and to the left, and then up here we have an upward and to the right arrow. Right? So those two would sum vectorially. And then down here at this intersection point, up and to the right, down and to the right. So when I sum those, the vertical components are going to cancel. And for this top one, I'm just going to be left with a horizontal component pointing to the left. For the bottom one, again, the vertical components are going to cancel. And I'm just going to be left with a B field pointing to the right. So this is confirming, right? Just kind of using a spatial argument here, thinking about this as vector. These are vector fields, that this is going to confirm that I will have above the plane, I will have a B field directed to the left, and below the plane, I will have a B field that's directed to the right. So that's pretty cool. So we confirm the directions, and now we actually want to find that B field. So we need to make our choice for Amperian loop here. And kind of like with Gauss, you think about the symmetry of the situation here, and you want to make your life really easy. So like with Gauss, I would say here, either go make your scalar product kind of an all or nothing situation if you can. So what I would probably do for that is I would choose something where I could have my Amperian loop go right along B, and then make a little right angle here on those sides. So basically the top and bottom of the Amperian loop, that box, that rectangle shape, all along the top and bottom, the path is going to go right along with B, and I'll make my integration direction go in the same direction as B, just to not have a sign issue there. So that'll be totally parallel to B along the top and bottom sides, and then, along the top and bottom, and then the left and right sides, you can see there that I know, for instance, my B field is going to be like this, right? So I've got 90 degrees there between DS and B. So let's remember that it's DS that we're talking about here along our integration path. Cool. So I've got 0 angle between DS and B along the top and bottom sides here. And then I have 90 degrees difference, but on the left and right, so no contribution at all there. So yeah, anytime you can get an all or nothing kind of scenario, that's what you want for these cases. So my b dot ds here is just going to be from the top and bottom sides. And I can, if I need to define my rectangle here, so I can define this dimension here as L. And I can define this dimension here as H. I'm not going to need that because I'm not going to use it, but it's good form to totally define your Amperian loop. So for my non-zero parts there, I'm just going to have BL from the top, right? Plus BL from the bottom. So that just gives me 2BL. The sides don't contribute there at all. And when I add up all my DS's along the top and bottom, then that's just that length L there. Okay, so that's the B dot DS side. Now I want to think about the mu naught I enclosed side. So as with Gauss, I encourage you to just look at this one side at a time, solve it, each one, and then put them together. So my mu naught I enclosed here, that's going to be mu naught times the linear density, lambda, multiplied by the linear amount I'm enclosing. So I'm enclosing a linear quantity L. So mu naught lambda L is going to give me my mu naught I enclosed. So remember here that lambda is our linear current density. So that's current per unit length. Back with Gauss, we used it as charge per length. And now in this context, we're using it as current per length. So I've got both sides of Ampere's law. I can put those together now. So the left side, the B dot ds side, is 2BL. I set that equal to the right side, which is mu naught lambda L. My L's are going to go away. That's good news, right? L is something that I introduced for my imaginary Amperian loop. It can't really have an impact on the situation, right? On the physical situation. That would be weird for my imaginary loop to have an impact on the natural situation. So I expect those L's to go away. And then I can solve for B. And I'll just get mu naught lambda over 2. So what we'll notice about B in this case, and here I'm just going to give a magnitude. The directions are as shown in the diagram. If I'm above the sheet, to the left. If I'm below the sheet, it's to the right. So you'll notice that there's no R dependence here. And you might remember that when we were looking at charged sheets using Gauss, we also did not see an R dependence there. And that might feel weird to you, right? Like, how can it be that I'm getting farther away from something and it doesn't get smaller? That's just weird to us because of how we experience life, basically, in 3 space. And that's just because this is an infinite sheet. So remember that we were given an infinite conducting sheet here. So no matter how far you go away from it, like as you go farther away from it, you can think about that you have like more of a subtangent angle that's contributing. So it all evens out, and no matter how far you are away from this thing, you still end up with a uniform B field. And so then you might ask, like, why is this at all useful? Because no one's going to make an infinite conducting sheet ever in the world. You're right. But the reason this is useful is that even if you have a non-infinite sheet, like just a conducting sheet, if you're close in to that sheet, this will be the behavior of it. So that you can, when you're producing technology and you want to create a situation where you have some kind of uniform B field, and you're like, how can I create a uniform B field? This is a way, and this field will the characteristics will be overwhelmingly uniform within certain tolerances, right? So you know that you can create a field that will behave like this as long as, fill in the blank, you have enough current going through, it's big enough, you're close enough to it, it'll still have this overall behavior.